Good afternoon or good evening, dear student or viewers, and welcome to this second part of our Trigonometry Refresher course or series. Last time we derived the formula 1, cos squared theta plus sine squared theta equal to 1, and we use this rotation transformation to derive formula 2,3, that is the cosine of the sum of angle, the sine of the sum of angle, and similarly for the difference. And for the difference, I suggested either we perform the rotation of the difference, or what we could still do is to replace theta with theta 2 with negative theta 2, and use the fact that sine is an even function. Cosine is an even function and sine is an odd function, which we use as a result, but we did not prove it. But that can be proven. We will do that. That can be proven here directly by taking anyway, we will do that. We can prove it. We will do it very soon. And we also derive the formula for the double angle, formula 4 and formula 5. We use that to also derive formula 6 and 7. And we show that we can also use Euler's formula and Pascal triangle, that is the binomial expansion, to compute the cosine or the sine of multiple angles. We did it for triple angle, and for the triple angle or any angle, you can still use this formula and perform it many times. But just imagine that you have a very large angle. It will take time, so the simplest way is to use the binomial formula and the Pascal triangle to get a coefficient, and write that the real part of the left hand side is equal to the real part of the right hand side, and similarly the imaginary part of the left hand side is equal to the imaginary part. So that's what we did to get cosine 3 theta and sine 3 theta. So we can do the same thing for any angle. So since we are not far with the computation for the double angle, so we will continue today with half angle using this result directly. So for half angle, we can see that we can use these two formula. We can use these two formula to compute. If you substitute, for instance, here theta equal to theta by 2, here we have theta by 2 in the right hand side, and therefore from there we can compute the cosine and the sine of half angle. So what I would do, I will copy this, and we will take it from there. Okay, so from this formula, we can extract, so from 6, so from equation 6, we have, if we substitute theta with theta by 2. We have cosine theta will be equal to, so we don't actually need a parenthesis when we have only one argument. Of course, one argument without multiplication whatsoever. That would be 1 minus 2 sine square theta by 2. So this is what we have. And from this, we can write directly, we can extract the sine from this expression. So this implies that sine, take the sine to the left and cosine to the right. We have 2 sine squared theta by 2 is equal to 1 minus cosine theta, and from this we divide both sides by 2 and we apply the square root. So okay, let's do it step by step. So we have type sine square theta by 2 will be equal to 1/2, or we can still write cosine 1 minus cosine theta divided by 2, and finally we can find sine of half angle, that is of half theta, will be equal to plus or minus the square root of 1 minus cosine theta by 2. So similarly, okay, we can denote, we can call this, this was equation 7, 8, okay, so we could have also called this maybe 9. So I'm going to write, I'm going to call this 10. So similarly, we can express cosine from equation 7. So from equation 7, we have cosine theta equal to 2 cosine square theta by 2 minus 1, from which we can extract, okay, let us write, so we have 2 cosine square theta by 2 will be equal to cosine, or 1, plus cosine theta. So cosine square theta by 2 is equal to 1 plus cosine theta by 2. So finally, if we take the square root, cosine theta by 2 is equal to plus or minus square root of 1 plus cosine theta by 2. And this is equation 11. So we can box these two equations, and we are not yet done. So we also need the half angle for the tangent function, because I've been omitting the tangent function. So we know that tangent, okay, let's write a few property for the, or identity for the tangent. Since we know that the tangent of theta is equal to sine theta by cosine theta. Okay, so from equation 1, if you remember equation 1, equation 1 reads cosine squared theta plus sine squared theta equal to 1. So if we divide both sides by cosine, because we want the ratio sine by cosine, so this implies that 1 plus sine square theta divided by cosine square. We divide by cosine square. That's what I wanted to say. I think I say sine cosine. This will be 1 by cosine square theta. But this is the tangent. This is 1 plus tangent square theta equal to 1 by cosine theta square. But this has a name. We call this sec function. So we define the sec function. Sec function to be 1 by cosine theta. Oh, sorry, that is sec of sec theta so sec theta is equal to this. So this is our definition. So from this equation, if I call this star, so from star we have that 1 plus tan square theta is equal to sec square theta. So we can call this equation 12, which we can also box. And similarly, we can define the cotangent function. Sorry. So we can define the cotangent function. Cotangent, we can just write cot like that. So cot theta by definition is 1 by tan theta, of course, which is cosine theta by sine theta. So if you use this same equation 1, and we divide by sine, because we divide by sine on both sides. So I can just say that from equation 1 we have, if we divide both sides by, we have cosine square theta divided by sine square theta. So we divide by sine square theta, and sine square theta divided by sine square theta is 1, but we can still write it. Sine square theta, this is 1 by sine square theta. So this gives us, you can write that in the next slide. So this gives us we know already that this is cotangent square theta, because cotangent is cosine by sine, and since we have square, we can raise all to the squared, so plus 1 is equal to 1 over sine theta all squared. So if we also define this to be cosec, because remember last time we defined sec to be 1 over cosine, now we can also define 1 over sine to be cosec. So this, and cosec, we just write CSC, just to keep 3 letters. Square theta, of course, where we define cosec theta to be 1 by sine theta. So actually double star, we can simply write it cotangent square theta plus 1 equal to cosec square theta, and this is equation 13, if we are 13, which we can also box okay. So at this stage we are not done with the with half angle, unfortunately. I just mixed. In fact, defining all this was because of the tangent. We want to compute the half angle of the tangent, angle of the tangent function. So back to half angle. Okay, so we define, we know already that the tangent of theta by 2 is sine theta by 2, and we've computed already this by cosine theta by 2. So this will give us, after these two formulas that we computed here, we take these two ratios, the sine and the cosine. So if we take the ratio, this divided by that, we will use the identity, the following identity. We know that if we divide square root of a by square root of b, this gives us square root of a by b. Okay, but this a, if we replace a by 2 and b by 2 like this, we write the same thing here, the same thing there, and the 2 can cancel out, right? So this still gives us square root of a by b, because they are divided by the same ratio. They cancel out. So if I write that directly, if I write that directly, I write the ratio have plus or minus square root of 1 minus cosine theta by 1 plus cosine theta. So we can write that directly. So the formula gives us plus or minus square root of 1 minus cosine theta by 1 plus cosine theta. But this is not enough. This formula with the square root is really a bit annoying. We can simplify this further. So we will denote this by 14, but we are going to simplify this expression, and for that purpose we are going to manipulate the formula, the trigonometric formula. Let's manipulate this expression. So we will still use formula 1. If you recall formula 1 states that cosine square plus sine square, or sine square plus cosine square, depending, equal to 1. So I can express either. So I can write that I can take cosine to the other side. So this implies that sine square theta is equal to 1 minus cosine square theta. But 1 is the same as 1 square. So we have the difference of 2 squares. And we know that if we have the difference of 2 squares, we can write this as 1 minus cosine theta into 1 plus cosine theta. So from this one, we can write, because in this expression we have 1 minus cosine theta and 1 plus cosine theta. So from this expression, we can extract 1 minus cosine theta or 1 minus sine theta in terms of sine square. So if we do that, we can write that 1 minus cosine theta is equal to sine square theta by 1 plus cosine square theta, cosine theta. Or we can do the same thing. Instead of expressing 1 minus cosine theta, we can write 1 plus cosine theta. And this will still be in the numerator, sine square theta divided by 1 minus cosine theta. So we have these two expressions. Now it will depend on which one we want to use. Okay, from this, let us use one of them. Now you can see that if you want to write this expression, we will divide both sides with 1 plus cosine theta, right? So if we do that, we have 1 minus cosine theta by 1 plus cosine theta. This will be equal to sine square theta divided, let me write it properly, it doesn't appear. So this is sine square theta divided by 1 plus cosine theta square. Or here also, if we divide both sides by 1 minus cosine theta, 1 minus cosine theta, this will be sine square theta divided by 1 minus cosine theta all square. like that. So we have these two formula that will allow us to express this ratio. So now we have this expression. This expression will give us the square root of 1 minus cosine theta, and if you take the reciprocal of this, it will also give us the same. Okay, so let me repeat this so that we can apply simultaneously these two. So we have this expression. So it implies that we have this expression, or, so I will do the same thing here. Now I will take the reciprocal of this second part. We have 1 minus cosine theta by 1 plus cosine theta is also equal to what? 1 minus cosine theta square by sine square theta. Alright, so what I want, I have a square here and I have a square there. So we can write that in one go. So what we can write, we can say this one is sine theta by 1 plus cosine theta all square. So this expression is equal to this 1 minus cosine theta by 1 plus cosine theta, and this same expression here is equal to what? To 1 minus cosine theta by sine theta all squared. Now you see that if I take the square root of this, we will get plus or minus square root of this expression. Similarly, square root of this is plus or minus square root of that. And plus or minus square root of this expression is tan theta by 2. So we can write that in one go. So finally we obtain that tan square theta, which is plus or minus this expression 1 minus cosine theta by 1 plus cosine theta is equal to this sine theta by 1 plus cosine theta, which is equal to 1 minus cosine theta by sine theta. So this is the final formula that we can box. And so this 14, actually I can call it prime here. Sorry. I can call that 14 prime. But this is our actual 14 because it groups everything. So this is our formula 14 for the half angle of 10 square theta by 2. Sorry, there's a theta by, no, that's not square. That is 10 theta by 2. 10 theta by 2. Sorry for that confusion. So this is 10 theta by 2. That is the half angle, so it's equal to that expression. Good, so that is it for the half angle. We have come to the end of this part of the lecture. Thank you for your attention and see you soon for the next part.